This is Daniel Cusbury, and we're going to continue looking at some fundamentals of probability. This video is going to center on conditional probability and what that idea is, and introduce the multiplication rule, which is going to help us find some more complex probabilities. So let's go ahead and get started. Conditional probability is the probability of the occurrence of one event, let's call it A, given that the other event B is known to be true or has already occurred. So we're going to be talking about complex probabilities now because we've got two events still. These are kind of like the A or B, two events that we're thinking of together. And the occurrence of one event, let's call it B, is going to affect the chance that A happens or not. And this is not a very new idea. We've got a concept of events being related to each other, and so if two things haven't happened yet and one of them does, it may affect the likelihood that the other one happens. That's kind of what we mean by conditional probability. So conditional probability is defined in the following way. The probability of A given B, so we read this vertical bar as the word given. The probability of A given B is equal to the probability that A and B both happen divided by the probability that just B happens regardless of A. So this is we'll treat this as a definition. This is A given B, and this little bar means given. So we can talk about the chance that A happens given that B has already happened is equal to the probability they both happen divided by the probability that just B happens. And so that's how we'll read that. So let's put this definition into practice in this problem. Considering the following table, which presents the number of U.S. men and women in millions, 25 years and older, who've attained various levels of education. So here's just the numbers, and they're divided by their highest level of education, and they're also divided into men and women. And we're asked, we're going to select a person at random from this group, and we're asked what's the probability that the person we selected has a bachelor's degree given that he's a man. So we're going to do a conditional probability now. We're going to try to find the probability that the person we select has a bachelor's degree. I'm just going to abbreviate it like that, given that the person is a man. So if we already know, we're getting a man out of this group, what's the chance that the person has a highest degree as a bachelor's degree? That's kind of another way to say it. If we already know we're getting a man, or given that we select a man, what's the chance they have a bachelor's degree? And I'm going to go ahead and start by writing the definition. So this is the probability that they both happen, so that we get someone who has a bachelor's degree and is a man. We can find that. Divided by the probability that we select a man from the group. So that would be the B part in the bottom, and this would be the and part in the top. So what we need to do to find conditional probabilities is we've got to find, this is called a joint probability. It has and in it, so find the probability they both happen jointly together. We can find that from this table. And then we'll find the probability that we just pick a man if we were to randomly pick one person from this group. So neither of those are going to be too hard to find. I'm going to need a little bit more room. So I'm going to find each one of those separately, and then I'm going to come back to the conditional probability. So let's start with the probability that I pick someone from this group with a bachelor's who is also a man. And to find that, I'm going to need the total group size down here, which I think is 25 million. I'm sorry, that's not the total group size. That's the breakoff for. So I'm going to need to find the total group size. I'm going to need to add all these numbers together to get my denominator. And then the numerator is going to be the number of people in this group who both have the highest degree as a bachelor's and are also men, and that'll be a really easy number. In fact, that number is right here. So this is the number of people in the group whose highest degree is a bachelor's who are also men. That'll be my numerator, 17.5. My denominator is going to be the total number of people in this list, and I can find that by adding all these things together. So I'm going to start from the left, and my calculator is kind of covering up some things, so just bear with me. That's the not a high school graduate. This is the high school graduate column. This is the some college, no degree. This is the associate degree. This is the bachelor's degree. And this is the advanced degree. This will be my N. When I add all these numbers up, I get 195 million people in the sample. So that's going to be my N that I divide by 195. And so now I can compute the probability that I randomly pick some person from this group and their highest degree is a bachelor's degree and they're also a man. And that's going to be 0.0897. So that's the numerator. So when I come back to this conditional probability, I've already got my numerator. It's going to be this probability that I select somebody from this group who's got a bachelor's degree and is also a man. And we're assuming their highest degree is a bachelor's degree. So these folks would have bachelor's degree too, but we're just interested in their highest degree. So now I'm going to find the probability that I select a man from this group. This is also pretty easy to find because all the men are in this blue row, all the women are here. So if I get this total, that'll tell me how many men are in this group out of the total, and I can find that. So I'm going to need to do some adding again. Sorry, I got my calculator covering up things. So I'm going to do, that's my men who are not a high school graduate. These are my men who are high school graduates. These are my men who have some college. These are my men who have an associate's degree. All right. These are my men who have a bachelor's degree. And these are the men who have an advanced degree. So that's going to be the total number of men in this group, 94 million. And then the total number of people in this group are 195. So this is kind of reasonable. We'd expect this to be close to half in this sample that we have. You know, not exactly half, but close to half of them are men and half of them are women. That's going to be a nice expected number. So we're going to do 94 over 195, and I get 0.4821. So I found those two probabilities without using anything fancy. I just used this table, and I put the proportion of people in this group, and that's my probability, the proportion of people in this group, and that's my probability. And now that I have both of these things, I can find the conditional probability using the definition. So put the probability, you get someone with a bachelor's degree as their highest degree and is also a man, divide it by the probability that you get a man, and you've got your answer. So the probability that I select somebody whose highest degree is a bachelor's degree, given that they're a man, is going to be 0.0897 divided by 0.4821, and that should also be a probability, something between 0 and 1. And I get 0.1861. That's my answer. So you'll see these problems are a little bit more complicated because I had to find these two parts before I found the actual answer I'm looking for. But I hope you see that finding each of these parts is not terribly hard to do from a table of data. So this is finding the conditional probability using the definition by finding the and probability, and then finding, this is the one that's given already, should be the one in the denominator. So make sure you get that straight when you're setting up problems like these. Okay, so now that we have conditional probability, we can actually develop a way to find more complicated and probabilities. So in a different video, I looked at finding the probability of A or B. That's using something called the addition rule. So this is not in this video, this is a different one. But we looked at the addition rule that can help us find these. Now we want a rule that's going to help us find the probability of A and B. And that can be found from this definition. If you want to imagine doing a little bit of algebra with me, we've got the probability of A and B here, and we want an equation just to find that. Well, imagine moving this thing over to the left side of the equation by multiplying by the probability of B on both sides. We can do that using algebra, and it cancels out here, and you got probability of A and B by itself is equal to the probability of A given B times the probability of B, and that's where this rule comes from. So this is the general multiplication rule. The probability that A and B happen at the same time is the probability of A given B times the probability that B happens by itself. Of course, A and B happening at the same time, like this order can switch because they're happening at the same time. So this could easily say the probability of B and A, or A and B. It's saying the same thing. So we could easily kind of switch the ideas here and say the probability that A and B happen at the same time is equal to the probability that B happens given A times the probability of A. So this is also the general multiplication rule. And you can find the joint probability, the chance they both happen, using it this way or this way. And sometimes you just pick one depending on which probabilities are easy to find. So sometimes when you're looking for and probabilities, you've got to find the conditional probability plus the probability that one of them happens all by itself. So you're still finding two things just like that last example, but I'm going to show you how to use this general multiplication rule in an example. So in the production of a particular product, approximately 1% of the items produced are defective. A diagnostic test exists to test whether or not a product is defective. If the product is defective, the test will identify it as defective 94% of the time. So this test is going to be imperfect. But we know if the product comes out being defective, the test is going to catch it 94% of the time. If the product is not defective, the test will indicate it as being not defective 98% of the time. So it's still not perfect, even if the product's fine. So this would mean this test can sometimes come out with like false positives or false negatives, as with most tests. And we know the chance that it's going to be right if it's defective. We know the chance it's going to be right if it's not defective. And these two numbers, this 94 and 98% are conditional probabilities. We know they're conditional because you have this word if leading into it. So if we know the product's defective, or given the product's defective, this is the chance that it's going to be right. If the product's not defective, do you see that kind of conditional idea? If it's defective or if it's not defective, what I've underlined in blue are the conditions. They're the things that are given. They're the events that given this event, the test is going to do this. Given that event, the test is going to do this. So they're conditional probabilities. And I'm saying with this information, we can compute the probability that a product, let's just say product, is identified as defective and is actually defective. So we want to find the chance that when we produce a product, it is doesn't work right, and the chance and the test is going to say it doesn't work right. So the product, the chance that the product is defective and test says defective. And using the multiplication rule, this is the chance that the product, let me say it like this. I can actually do this in any order I want. I'm going to do the chance that the test is defective given the product is defective times the probability that the product is defective. So I can do that. The way you know you're doing the multiplication rule right is the given part should be the same as the second probability, the one that's all by itself. So if you get those switched up, you've done the multiplication rule wrong. So I want to find the chance the test is defective given the product is defective, which I think that's given to me. Let me just clarify this a little bit. This is the chance the test says it's defective. So it comes back saying it's defective. Given the product is defective, and then the chance that the product is defective just by itself, regardless of the test. And I think that's in the problem too. So given that the product is defective, the test is going to come back saying it's defective 94% of the time. So let's see, let me just read the sentence again and make sure we can agree that that's what this probability is. If the product is defective, so given it's defective, the test will identify it as defective 94% of the time. So the chance it says it's defective if the product's defective is 94%. I'm going to write that as a decimal, 0.94. Okay, so you should be okay with me saying this conditional probability is the number 0.94. And then the chance it actually comes out being defective, regardless of the test, is given to me in this first sentence. In the production of a particular product, approximately 1% of the items produced are defective. So I don't care what the test says for this one. I'm just interested in the chance that it comes out being defective, and I'm told that's about 1%. So I'm gonna write that as a decimal too, 1%. And I'm going to use that to find my probability that both of these happen at the same time. So the chance they both happen at the same time are 0.94 times 0.01, which is 0.0094. So that's my chance that I produce a defective product and my test catches it, which is pretty small, but it's not that much smaller than 0.01, which is the chance that I produce a defective product. So that's an example of how you use the multiplication rule to find and probabilities. You have to identify the conditional probability and then the probability of the given one all by itself. So remember, these two events have to be the same. The one after the bar and the one that's by itself have to be the same, or you've switched something up. Okay, so we can find some other things with this information using what's called a tree diagram. So I have in this slide the diagram made from the exact same situation that we just worked with. And because we're doing multiplication, you can see that, like in this last slide, we're taking two probabilities and multiplying them by themselves. A tree diagram is formed by imagining two events happen like simultaneously or sequentially. And if we know like how they're related to each other, we can compute some of these joint probabilities pretty quickly. Okay, so let me just kind of explain what we're looking at. This first two branches represent what I'm calling event one, which is the production of the product and whether or not the product is defective. Okay, so we know from the problem on the last slide that when we produce a product, there's a 0.1 chance that it's defective, so that's what that means. There's a 99% chance it's not defective. So from the moment of production, there's a 0.1 chance that this happens, 0.01 chance this happens, and a 0.99 chance that this happens. Event 2 is displayed by the second set of branches, and event 2 is what the test is going to do, and the chance it's going to do that. And event 2 is based entirely on, or the chance that event 2 does certain things is based on whether or not the products are defective or not. So if it's defective, then there's a 94% chance it says it's defective. There's a 6% chance it says it's not defective. If the product isn't defective, there's a 98% chance it says not defective and a 2% chance that it's wrong and says defective. So you see, so this second group of branches is dependent on the first two branches, which is why these numbers are attached to their appropriate branches. So this is the nice visual in a tree diagram is you can kind of follow these branches. And you can see there's actually 4 different outcomes when you produce an item. It's defective and the test says defective. It's defective and the test says not defective. It's not defective and the test says defective. And it's not defective and the test says not defective. And we also know from the multiplication rule that if we want to find the probability that any 4 of these events happen, meaning this one and that one would be one event, this and that would be another event, this and that would be another event, this and that would be another event. We can just multiply the numbers on the branches together. So we just follow a particular path to find the probability. For instance, what we just did is we found the probability that a product is defective, which meant I followed this branch. And then we also found the probability that it said defective. So both the product is defective and the test came back defective. And we found that probability by taking 0.94 and 0.01 and multiplying them together. And we got 0.0094. And that's how we found that, because we have the multiplication rule. So the multiplication rule says multiply those two numbers. If I also wanted to find out, so maybe I'm like checking if my my test is a good test and I want to see like the chance it's right. I may also want to find out what's the chance the product is not defective and the test indicates not defective. Well, that's the chance that can be found by multiplying these two numbers together. So this is the conditional probability, the chance that it says not defective if the product's not defective. And then this is the probability that it's not defective. So I'm using the multiplication rule again. And I can follow these branches, multiply these numbers together to get my probabilities. And let me just find that number real quick. 0.98 times 0.99, so this would be pretty big, 0.9702. So there's a 97% chance that my product is not defective, and my test tells me it's not defective, which is pretty nice. So if you're doing quality control and you want to see, the chance that your test is wrong or the chance that you throw out products that are perfectly fine, you can find any 4 of these probabilities. Let me just do one more, and I'll trust you can do the last one. I want to find out the probability that the product is not defective, but it says defective. This would be called a false negative. This is a false negative. It says it's bad, but it's not. That's going to be the chance the test indicates not defective, given that it's not defective. So this is the conditional probability. This depends on that. See, these numbers are different if it's defective. This number is specific to it being not defective. And then times the chance that the product is actually not defective. So let me find that real quick. And you can find the last one on your own. So this is going to be 0.02 times 0.99, which is 0.0198. So this is the chance that I get a false negative on my test. So if you've got a few options for tests and you're trying to judge whether or not your test is a good test, one number you might be interested in is how many false negatives am I going to get? Like how many good products am I going to throw out because the test says it's defective, but it's not defective. And so this is under 2%, which may be acceptable. Maybe it just depends on what you're doing. So this is an example of how to compute a lot of and probabilities pretty efficiently, because you've got your one event here breaking into 2 parts, and then you got your other event which breaks each thing into 2 parts. And the multiplication rule says you can follow these branches and multiply those 2 numbers together to get your joint probabilities. So that's a nice application of conditional probability to find a lot of different more complex probabilities.